Aluminum is one of the most versatile metals in the world. It's as malleable as paper, yet as tough as steel. But have you ever wondered how a massive block of solid aluminum is transformed into the ultra-thin foil found in your kitchen? Let's dive into the fascinating process behind the production of aluminum foil. One of the most widely used household materials today, aluminum foil was first invented by a Swiss company in 1911, originally used to wrap its famous Toblerone chocolate bar. Over time, its unique properties, such as the ability to completely block light, heat, and moisture, made it indispensable in food packaging, cooking, and beyond. For centuries, scientists struggled to isolate aluminum due to the complex nature of its extraction. Even when they succeeded, they could only produce small amounts of aluminum powder, making it rarer and more valuable than gold at the time. The real breakthrough came with the discovery of electrolytic reduction, revolutionizing aluminum production. But before we get ahead of ourselves, let's start at the very beginning. The primary raw material used in aluminum production is bauxite. Is bauxite a mineral rich in aluminum oxide? While aluminum can also be found in clay, extracting it from bauxite is far more efficient, making it the preferred source. Typically, bauxite is mined in open-pit operations and then transported to refineries for processing. These mines are mostly located in tropical regions, with one of the largest being the Waipa mine in Australia. This massive site alone produces an astonishing 30 million tons of bauxite every year. Once extracted, the next step is refining. The process begins with the bauxite being mechanically crushed before being mixed with caustic soda and processed in a grinding mill, a watery suspension of finely ground ore particles. The slurry is then pumped into a digester, a high-pressure tank that functions like an industrial pressure cooker. Inside, it is heated to temperatures between 230 degrees Fahrenheit. The mixture remains under these conditions for anywhere from 30 minutes to several hours, allowing the caustic soda to break down the ore efficiently. Additional caustic soda may be introduced to ensure the process is as effective as possible. At this stage, all aluminum-containing compounds dissolve into the hot slurry, forming a sodium aluminate solution. This solution then passes through a series of flash tanks where pressure is reduced and heat is recovered for reuse in the refining process. Next, the slurry is transferred to a settling tank, where it is left undisturbed. As it settles, impurities that do not dissolve in the caustic soda sink to the bottom. This residue, known as red mud, consists of fine sand, iron oxide, and trace oxides of elements like titanium. Once these impurities have settled, the remaining liquid, which has a dark coffee-like appearance, is pumped through a series of cloth filters. These filters trap any remaining fine particles, ensuring a purer solution. The trapped material is then washed to recover any remaining alumina and caustic soda, which can be reused in the process. The filtered liquid is now ready for the next stage, precipitation. It is pumped into a series of towering, 6-story high precipitation tanks. Inside these tanks, seed crystals of alumina hydrate, alumina bonded to water molecules, are introduced from the top. As they descend through the liquid, the dissolved alumina begins to attach to them, causing the seed crystals to grow in size. As alumina attaches to the seed crystals, they gradually grow in size and eventually precipitate out of the solution. Once removed, the crystals go through a washing process before being transferred to a kiln for calcining, a high-temperature treatment that removes the chemically bonded water molecules from the aluminum. A screw conveyor continuously moves the alumina crystals into a rotating cylindrical kiln that is slightly tilted, allowing gravity to help transport the material through it. Inside, the kiln reaches temperatures of 2000 degrees Fahrenheit, 1100 degrees Celsius, driving off the water molecules and leaving behind dry anhydrous alumina crystals. These crystals then pass through a cooling system, preparing them for the next stage, smelting. To extract pure aluminum from alumina, the strong bond between aluminum and oxygen in the aluminum oxide must be broken. This is achieved through a process called electrolytic reduction, commonly known as smelting. The process takes place in a steel vat called a reduction pot. The bottom of the pot is lined with carbon, which serves as the cathode, conducting electricity through the system, are suspended and lowered into an electrolyte solution. These anodes remain about 1.5 inches, 3.8 centimeters, above the surface of the molten aluminum, known as pot lines, each consisting of 50 to 200 pots connected in series to create an electric circuit. A single pot line can produce between 66,000 and 110,000 tons. Within the reduction pot, aluminum crystals dissolve into molten cryolite at extremely high temperatures, ranging from 1,760 degrees Fahrenheit to 1,780 degrees Fahrenheit. This forms an electrolyte solution that enables electricity to flow from the carbon anodes above to the carbon-lined cathode at the bottom of the pot. As an electric current passes through the cryolite, a solid crust forms on the surface of the molten aluminum. Periodically, additional alumina is stirred into the mixture, breaking the crust and allowing it to dissolve. Once in solution, the alumina undergoes electrolytic decomposition, separating into pure aluminum and oxygen. The aluminum settles at the bottom of the smelting cell in molten form, while the freed oxygen bonds with the carbon anodes and is released as carbon dioxide gas. Once purified, the molten aluminum is drawn from the smelting cells and transferred into crucibles, then poured into furnaces for further processing. At this stage, other elements can be added to create aluminum alloys. Aluminum foil is typically made from 99.8% to 99.9% pure aluminum to ensure its unique properties. The liquid aluminum is then poured into direct chill casting devices where it rapidly cools and solidifies into large slabs called ingots or roll stock. These ingots undergo a series of mechanical processing steps to reduce their thickness and transform them into aluminum sheets. The process begins with hot rolling, where the ingots are first heated and then passed through a series of rolling mills that gradually reduce the metal's thickness. This step may be repeated multiple times, depending on the desired thickness and properties of the final foil. After hot rolling, the aluminum sheet undergoes cold rolling, where it is passed through a series of rollers at room temperature. This process refines the sheet further, achieving the precise thickness and surface finish required for aluminum foil. Cold rolling also increases the tensile strength and hardness of the metal. Between cold rolling passes, the aluminum sheet may undergo annealing, a controlled heating process that relieves internal stresses and enhances its flexibility. To enhance its formability, the aluminum sheet undergoes an annealing process, where it is heated to soften the metal and relieve internal stresses introduced during cold rolling. This step improves the sheet's flexibility, making it easier to shape into its final form. At this stage, the foil rolling process begins, a highly precise operation aimed at achieving the desired thickness, surface finish, and mechanical properties. The cold-rolled aluminum sheet is fed through a series of specialized foil rolling mills, where multiple rollers gradually reduce its thickness. These mills ensure uniform thickness and a smooth surface finish, both critical for high-quality foil production. To further refine the foil, tension leveling is sometimes used, where the foil is stretched over a series of rollers to eliminate imperfections and maintain consistency. During the rolling process, a thin layer of oil or lubricant is applied to minimize friction and prevent the foil from sticking to the rolls. In some cases, intermediate annealing is required between rolling stages. This additional heating step helps maintain the foil's ductility, preventing it from becoming too brittle while allowing for further reductions in thickness. Once the aluminum foil reaches the desired thickness, it undergoes final annealing and finishing to enhance its properties and ensure consistent quality. The foil is heat-treated in a controlled environment to relieve any remaining stresses, improve flexibility, and optimize its mechanical characteristics. The wide foil sheet is then cut into narrower rolls, which are the standard commercial sizes used in households and industries. Throughout the production process, the foil is subjected to rigorous quality control checks to ensure it meets strict specifications for thickness, tensile strength, and surface finish. To determine thickness, a sample is weighed and its area is measured. The thickness is then calculated by dividing the weight by the product of the area and the alloy's density. Tensile testing is another crucial step, but it must be carefully controlled since factors such as rough edges and small defects can affect the results. In this test, a foil sample is placed in a grip and a pulling force is applied until the material fractures. The force required to break the sample is recorded as a measure of its strength. Once production is complete, the aluminum foil is wound onto large rolls. and then cut into various standard size rolls or sheets based on customer requirements. The finished foil is packaged and labeled for distribution to manufacturers, retailers, and end users worldwide. An important aspect of aluminum foil production is its high recyclability. Scrap aluminum from the manufacturing process, as well as used aluminum products, can be melted down and reprocessed into new aluminum products, including foil. Recycling is an energy-efficient process that significantly reduces the environmental impact of aluminum production. And that's how aluminum foil is made. It's fascinating to see how much effort goes into producing such a seemingly simple household item. But did you know that making beer is just as intricate? Here's how it's done.